Hello everyone, I'm Thandar Zaw Win. I came from Myanmar. Now I'm doing PhD in INDPLI from Physics Department. Under the guidance of Sabyasachi Ghosh, we are doing this graphene project.
I'm Cho Win Aung. I'm also one of the international students here. I'm also from Myanmar. We are doing this condensed matter physics things in INDPLI.
For last 1 year, our group started some theoretical research was on graphene topics. These are new topics. One of them is this shear viscosity expression for graphene system in relaxation time approximation. In our daily life, we already familiar that when the light bulb is connected to the power through wire, at that time electron is flowing inside the wire. From this figure, we can see that kind of flow called ballistic electron flow in matter. Electrons are just flowing simultaneously. The flow profile is Kamisa. The same thing we can do for graphene system. At that time, the unconventional flow is happening in this system. They call hydrodynamic electron flow in graphene because of graphene unit structure and properties. This unconventional flow was observed by a group of researchers from Weizmann Institute of Science, Israel, 2019. What they found that the transition of ballistic flow profile in low temperature into the parabolic hydrodynamic profile with increasing temperature via Hall electric field. They call Poisson flow. Actually, this Poisson flow is the hallmark of hydrodynamics. From our theoretical side, we calculated the shear viscosity, one kind of transport coefficient. Why we calculate this Poisson flow pattern entirely reflects the existence of viscosity. This shear viscosity is nothing, just kind of viscosity where there is a friction between different fluid layers flowing with different velocity. Mathematically, we can see that the shear flow is directly proportional to the velocity gradient. Eta is the shear viscosity coefficient. So, the velocity gradient greater, the shear force between fluid layer greater.
Okay, firstly, I want to explain the different energy momentum relation. The first one is the non-relativistic energy momentum relation. We can use this expression to express the motion of a particles on the plane, like the motions of vehicle on the road. And next one is the relativistic energy momentum relations. This expression can be used to depict the motions of the fundamental particles in relativistic matter, like the motions of quark in quark-gluon plasma medium. Unlike non-relativistic and relativistic energy momentum relation, there is a dispersion relation or energy momentum relation. This can be found on graphene. So its velocity is nearly the speed of light. It is 100 times smaller than the speed of light. Okay, let's go to the explanation of the shear viscosity to entropy ratio. We derive the shear viscosity coefficients from the dissipative mass of the energy momentum tensor and the entropy density from the ID pass of the energy momentum tensors. Finally, we get the shear viscosity to entropy density ratio. We will use this expression to compare with the non-relativistic and ultra-relativistic system. So before going to the explanation of our result, let's come and see the terminology of the derived fluids and Fermi liquids in two regions, both high energy physics region and also condensed matter physics. Here you see condensed matter physics domain is a very low temperatures and low chemical potentials. So we can say this is extremely low temperature case. So within this range, matter has Fermi energies of 2 to 10 electron volts. But for our interested layers of graphene, its chemical potential can be changed by a dropping method in experiment. So we can define derived fluids and Fermi liquids in these condensed matter physics domain, which mu by T values is very much less than 1 and very much greater than 1, something like this. And the same like we define here, so in high energy physics domain also we can define derived fluids region like in early universe QGP system or quark, and the cores of neutron star as their Fermi liquid region. Okay, let me explain the shear viscosity to entropy density ratio. This is a more important quantity to know the fluidity of the system. So for our graphene system, shear viscosity to entropy density ratios in terms of the temperatures, you can see here. So there is a lower values of shear viscosity to entropy density ratio, we call the KSS bound, which was deduced from the string theory based calculation, and then there is no experimental observation of shear viscosity to entropy density ratio for graphene. So we had taken this blue dotted line to tune our research finding. So by taking the two values of the Townsend values, our new expression of the shear viscosity to entropy density ratio showed that our graphene system is nearly close to perfect fluid system. Here in the last figure, we have plotted the shear viscosity to entropy density ratio in the two regions of Fermi liquids and derived fluid. So you can see our graphene values is coming from the Fermi liquids to derived fluid region. At that time, it began lower. So our here, this is because of the thermodynamic phase space part in the shear viscosity to entropy density ratio expression.